Hello everyone, welcome back to my channel. This is Hitesh Agarwal and today we're continuing our project. Today's topic is STP, so let's get straight into it. Today's agenda, we're gonna go over I'm gonna introduce what STP is. We're gonna discuss why is STP needed. I'm also gonna demonstrate a broadcast storm. Then I'm gonna introduce another feature of STP known as PVST, and then we're gonna start adding VLANs to a topology. So introduction to STP. STP stands for Spanning Tree Protocol. It's a protocol that runs on all switches that helps us solve loops, broadcast loops specifically. Well, why do we need STP in the first place? Um, when we have multiple switches linked together in a network, without STP, a broadcast storm can occur. And I'm going to display how that works. I'm going to show broadcast storm. Essentially, these broadcast storms occur because simple broadcast frames do not have a TTL segment in the packet, TTL time to live. So that frame will just loop forever in the network. STP helps us helps us stop these loops by blocking redundant paths and forcing all switches to only have one path to a root bridge. Now, a root bridge is a new term. It essentially stands for a root switch. The root bridge switch is a special bridge that at the top of the spanning tree. It essentially connects the entire network to the outside world, if that's how you want to set it up. It is also where every other switch in the network will start its calculation to calculate the best path to the root switch. How is the root bridge elected? As soon as all the switches boot up, they advertise themselves as the root bridge. After they have received all the advertisements from each other, they look for the lowest bridge ID in those packets. The packets are BPDUs. It stands for Bridge Protocol Data Unit. In those units, they look for the lowest bridge ID, which the bridge ID sums up to be the switch priority and the MAC address. The switch with the lowest bridge ID is selected as the root bridge, and every other switch calculates a route to the root bridge. So let me demonstrate how a broadcast storm works. I do not recommend doing this in an actual network, as it can cause network outages. I'm doing this on Packet Tracer. You can try it on Packet Tracer, but I would not recommend doing this on real hardware or on a real network. So we have ourselves 3 switches here. Right now, all these switches are running STP. So let's just first go and disable STP. So to disable STP in Packet Tracer, you have to enter this command: no spanning tree VLAN 1. Same thing for all the other switches. No spanning tree VLAN 1. No spanning tree VLAN 1. And you can see all the links are up. Previously, it was one of the ports was shut down here, but now it's all up. So let's demonstrate how a broadcast storm works. I'm gonna add 2 PCs here, and obviously gonna connect to them. I'm also gonna give them an IP address. So I'm gonna assign this IP of 1.1, and I'm gonna assign this one an IP address of 1.2. So let's try. Let's try pinging first. If you ping 192.168.1.2, you see we created an ARP request because we do not know the destination MAC address of PC1. So PC0 is going to send an ARP request And knowing it's an ARP request, it is going to be broadcast, going to be broadcast message. So it sends the broadcast message to switch 0. Switch 0 sees it's a ARP message and it will start flooding it. Oh, well, why didn't it do that? Let's see why I didn't do that. Actually, I think we may have already messed with switches, so we have to probably add new switches here. 160, 160, and 160. I connect them. I'm going to enter the no spanning tree command right now. No span VLAN 1. No span VLAN 1. And multi no span VLAN 1. And let's add the PCs here. Okay, so let's set up the IPs again. 192.168.1.2, 192.168.1.2. All right, let's try it again. Ping 192.168.1.2. Creates the ARP request, send it out. I think this guy's gonna cause the same problem again. Let me try again and open a new packet tracer file. This might be bugged. So I went ahead and made a new topology. This time I'm gonna do the no span command at the end. Again, 1. And now let's go straight to pinging. This is 1.2. Reset simulation. Oh, it's bugging. Wow. Simulation. Ping 192.168.1.1. And I'm also going to do only ICMP and ARP. So we know it's a broadcast message. It's going to send an ARP request to switch 1, and you can see it is creating packets, broadcast packets for everything. So it's going to send out all, to CC, it all flashed out like that. This is literally a broadcast storm right here. We are seeing all of these broadcast packets being sent to each other, and eventually it is going to be so bad that it will never be resolved. And we cannot do anything here. If you try, like perhaps doing something else, it will not work because the switches are busy resolving these packets. So that's practically what a broadcast storm is. Packet tracer has some issues with spanning tree. I've noticed that before as well. But That's practically what a broadcast norm is. This is just going to keep looping forever and forever. How do we solve that? Well, STP helps us solve that by blocking redundant paths. And how does it block redundant paths? We'll talk about that right now. We are going to add the 3 switches again. Okay, let's interconnect them. And here we can see if we just time skip, we see that this switch has taken up as the root bridge. So I'm going to move this up just to emphasize the spanning tree. Now, why has this switch taken up the root bridge? Well, there's a reason why, and the reason is, give me a second here. And the reason why it has taken a precedence over all the other switches is because it has the lowest bridge ID. Now, bridge ID, I've said before, is the priority in the MAC address. So let's confirm what the MAC address is here. To confirm, I'm going to do show spanning tree, and you can see here it says this bridge is the root, so it's the root bridge, and we also see the address here. Let's compare this address with every other switch. So switch 3 and switch 5. Let's open that and top that so we can all see it together. Same thing we're going to do here, in and show spanning tree. Same thing here, in and show span. So here we see that the address of the root bridge here says root ID. The address of the root bridge is 40AB, and as you can see, 40AB is the root bridge here. Same thing for its own bridge ID. The MAC address is 2A4B. 4B is, well, if you're comparing MAC addresses here, we start from the very first segment. The very first segment here is 0001, whereas here is 000D. So of course, this one 001 is smaller. Same thing over here. It says the MAC address of the root bridge, and we see its own address is 0009. Here is 0011, 0001. So it takes precedence over all the other switches in the network, and that's how it's elected as the root bridge. Now let's talk about the cost. What is the cost here? Well, when we have root bridge here, this is our root bridge. After it has been elected, it will send out a cost to each switch underneath it, or it will send out a BPDU to each switch, and in the switch, it will mention a cost. Cost from the root bridge is 0 on both sides. On both sides here, the cost will be 0 because that's what it is advertising itself. The cost is basically a metric for other switches to determine how many hops or how many hops away the root bridge is. So here it advertises to switch 3 and switch 5 the cost of 0. Switch 3 looks at the cost and it says, well, hey, I'm directly connected to the root bridge, but I'm going to add my own interface cost. And the interface cost for gigabit Ethernet ports is 4. And that's the default for every gigabit Ethernet. For 10 gig Ethernet, it's 2. For 100 megabytes is 19. So it adds the cost of the gig port, which is 4, to the main cost. So total cost, it will say, for me is 4. Total cost, it will say, for itself is 4. Same thing on the other side. This will take the cost and it will say, well, hey, I have all of the stuff. Same thing. Total cost is 4. On this interface is special because now it's two downstream switches talking to each other through BPDUs. They're going to talk the same thing. Well, hey, this time my cost, switch 3 is going to advertise a cost of 4 to switch 5, and switch 5 will say, well, hey, again, my interface cost for this port is 4. I was advertised a cost of 4. My cost from this port is going to be 8. Same thing when switch 5 says to switch 3. Well, here, well then how do we make a difference here so that we can elect a normal port? Like as you can see, one of the ports is down and one of the ports is up. Right now it's in a blocking state. And the way they determine which port to be blocking or forwarding is they would either do it through the lowest root cost. Right now, there's only two steps that they will look at for the difference. Right now, the total root cost is 4 on both or 8 on both on this interface on this network. So that is out of the question. It is a tie. The next criteria they look at is the lowest bridge ID between or amongst the two switches. So switch 3 and switch 5, lowest bridge ID. Let's see. Switch 3's bridge ID is 000D and switch 5 is 0009. So that's a tiebreaker. Here we have that 0009 is superior to 000D, so it is going to take precedence over switch 3. And switch 3 has to make its own port as blocking. As you can see, here is blocking, and the role of the port is alternate. Root port means that the port is directly connected to the or is connected to a designated port on the other side. If we check here, both ports are designated, which means that this is the one that is sending on all the BPDUs to the root ports, and this port, so in switch 5 has to be root port, and on this switch, that gig01 has to be root port. Every port opposite of the designated port has to be root port. Not really, actually. Sorry, that's not a reality because here we can see that this port is also a designated port, and this port connected to switch 5 is alternate. That's if it is not the root bridge. That's if it's not the root bridge. Yes. So that's how it calculates who to make the root bridge and every other port in the system. So now let's talk about PVST. So enter the PVST. PVST stands for per VLAN spanning tree. In a network where we have multiple VLANs, it is possible to run an STP instance for all PVST or for all VLANs. PVST allows us to manage a separate instance for each spanning tree, for each VLAN. It makes us, it allows us to manage a separate spanning tree instance for each VLAN. Another feature of PVST is that different switches can be the root bridge for different VLANs, and I'm going to demonstrate that in the topology. Also note PVST's default spanning tree for all Cisco switches. Once you start adding more VLANs, sorry, it will automatically switch over to PVST. So let's start adding some VLANs to our topology and configure different switches to be different root bridges. So we're back here in topology, same thing. Let's start adding VLANs to all our switches. Switch 4, switch 3, and switch 5. Let's just top all of them first. Switch 3 is the root switch, or switch 4 is the root switch. Switch 4, top it here, switch 3 in the middle, and switch 5. So I'm gonna make, well, let's just first add the VLANs of T, VLAN 10, VLAN 20, VLAN 30, and VLAN 40. I'm also gonna add all interfaces in the trunk link and allow all VLANs to go through. So interface range gig01 to 2, switchport mode trunk, and switchport trunk allowed VLANs 10, 20, 30, and 40. Same thing here. Conf T, we want to add the VLANs 10, 20, 30, and 40. And interface range gig01, 1 to 2, switchport mode trunk. And if you just want to add all the VLANs, you could also do this. You could do switchport trunk allow VLANs all, This just allows all VLANs. It's a cheap way to do it, but yeah, I like to do it this way because we get more control over what VLANs are allowed. But for the sake of time, we'll just do it this way. VLAN 10, VLAN 20, VLAN 30, and VLAN 40. Interface range gig01 to 2. Switchboard mode trunk. Switchboard trunk allowed VLANs 10, 20, 30, and 40. To confirm if the port has been added to trunk link, you could do show interface trunk, and it will show you all the interfaces that are in trunk and allowed VLANs. You can see allowed VLANs here. Same thing here, do show interface trunk. We have 110, 20, 30, 40, and do show interface trunk. And see 10, 20, 30, 40. To check what STP is running, we could check do show by do or show spanning tree, and we could do detail. You can see we have all of these things. We could check by different VLANs. We could do a summarization of it. We could check the details. So let's see the detail. Well, this is not what we want to see actually. Let's see summary. Let's see what kind of is running right now. We see is in PVST mode. PVST mode. So all of the VLANs are active. Root bridge for default VLAN 10, 20, 30, 40. We want to make our root bridge. We'll make VLAN 10 and VLAN 20 root bridge on this switch, and we'll make VLAN 30 and 40 root bridge on this switch. So let's configure that. So to configure that, we do spanning tree VLAN 20, VLAN 10, and we can do priority or root. Well, both can work, but there's a difference between both. What we want to do is prioritize this switch as the root bridge. So we do priority, and if we do that, you can see bridge priority in increments of 4096. 0 means it will never become the root bridge. The next hop will be 4096. So we wanted this to be 4096. Spanning tree VLAN 10 priority 4096, and VLAN 20 4096 as well. The other option that we saw, root bridge or spanning tree VLAN 20 root, is a way to configure a load balance or configure failover in case switch 3 was to go down or switch 4 was to go down, and they both were connected to same routers here. We could configure this to be the root bridge, and in case switch 4 goes down, switch 5 will take over VLAN 10, VLAN 20. So let's also configure that. It's a very nice feature. So root primary. As you can see, root, if we do root, we have two options, primary and secondary. So we do root primary. Same thing for VLAN 20. And we want to make sure that it also knows about the other switch and its VLAN. So VLAN 30, we want to make sure that it's root secondary. Same thing, root VLAN 40, root secondary. So now let's do it on switch here. Configure a load balance, I'll configure a priority. So spanning tree, VLAN 30, priority 4096. And VLAN 40, 4096. And now we're going to do VLAN 10, root secondary, and VLAN 20, root secondary. Now let's confirm the root bridges. Let's confirm it from this side, from switch 3, so switch 3's perspective. Let's first also display the MAC address. So show span. You want to see the MAC address of the bridge itself, and from this perspective, show span. Do show span. Show span. And let's start from VLAN 10. VLAN 10 is here. It's VLAN 10. Uh, the root ID here, 0001, and you can see root ID here is 0001. This bridge is the root bridge for VLAN 1 still. VLAN 10, this bridge is the root bridge. Same thing for VLAN 20. If you do 0001, 0001 is the root bridge for VLAN 20. For VLAN 30 and 40, as you can see, address 0009 and 0009. Same thing here. If you go to VLAN 30 and 40, address here 0009, which matches itself to its own. And as also says this bridge is the root, this bridge is the root. So we have successfully configured the two different switches to be different root bridges for different VLANs. Let's see if it fails over or not. So let's go on gig 02 and shut down. Let's go on switch 3, let's switch 4 and shut down. Actually, let's try this. Why not we just delete gig 02 or switch 4? See if that will matter. Let's see if that will switch over. Switch 4 gone. Switch 5, and if you see show spanning tree, we can see, well, it hasn't cleared its cache yet. Oh, well, it did. So as you can see, VLAN 10, this bridge is the root, this bridge is the root, this bridge is the root, and this bridge is the root. As you can see, we configure load balancing properly as well. That's basically what STP is. There's multiple spanning tree modes out there. There's normal STP, there's PVST, there's rapid PVST, which is fast convergence. There's also another feature known as MST, which is multiple spanning tree. It's more of a CCNP topic rather than CCNA topic, but it's also another great feature that I've worked with. But as far as our STP knowledge concerns us, and this is far farther than go. From next video onwards, we're going to start configuring routing, and we're going to start working on our actual network. We're going to use a different software. We're going to work with GNS3 because that's a software that I'm most familiar with. Apart from that, thank you guys for watching. I will see you guys next time.